let's think about what we have left to do. I know. We should do a yearbook. Okay, we'll do a picture day next on Thursday. So quick, form some clubs and stuff. We need club pages. So we have next week. Did I already do this? So the first thing is we have the intuition post-test. That's in lab next week. What are the dates? What's the date Monday? 9:30. 4? So 12:4 to 12:8. Okay, and this, if you do this test, you get 100% on lab exam 3. If you don't do it, I mean, anybody have a problem with doing it? Okay, good. If you don't, I don't know. Would I really give someone a 0 for, I don't know what I would do. Just try to come take it. I don't know. Those people just need to come talk to me if that happens. And then we have one more quiz, I think, right? Next Thursday? Oh, this Thursday. I think it's next. You have your syllabus in front of you. It says the 30th? Oh. I want to do what's on the syllabus. Okay. And then the last exam. And there are 2 times you can take this. You can take it Monday, 12/11 at 6 p.m. in S1326, or you can take it Thursday, 12/14 at 2 p.m. in S1328. And once you've done those 3 things, you're done with this class. Anybody have any questions about the end of the semester? Yes. Yes, it is, but I mean, if that ends up being too high, then I sort of curve it at the end, you know, but let's call that like, that's like the automatic A standard. And then there's, and then after that you adjust. That's how they do like national track meets and stuff. Like there's like an automatic qualifying standard and then a provisional standard. And like if you make the automatic standard, then you don't have anything else to worry about. If you make the provisional standard, then you have to wait and see. You know what I mean? So yeah, 92, you have nothing to worry about. Under 92, who knows? It depends on how the class does overall. You know what I mean? You can learn more about national track qualifying standards at ncaa.org. Yes. I only have one that I haven't given back yet, right? A lab test and a regular test, right? Two tests and a lab test? Is that true? Well, anyways, I'll get it back to you as soon as I can. Yes. No, not really. It's just going to be sort of the same as the other ones, but um, questions can be, it'll probably be like something like 2 questions from the newer stuff and 2 questions from older stuff. So you could sort of gamble on it, you know what I mean? But like, if you prepare for everything, then you're ready for whatever the question is. I think of it as sort of statistical sampling. Like like the more stuff you understand, the better your chances are of seeing something you understand. Yep. Yeah, probably. I mean, it's going to be the same length. If there are more than 4, then the questions have to be shorter. I intend it to be like an hour test or so. Any other questions? Okay. We are going to skip a topic. So now we'll skip something stupid and go right to something awesome. The thing that we're skipping is called conservation of linear momentum. No talking. Um, and the thing that we're skipping to is conservation of energy. So first, let's talk about what conservation is in physics or science. Um, okay, so let's say okay, so there's this lady. This is like a little tree. And here she has like a little shovel in her other hand. Really more of a trowel. And she has her hair's parted and she has like a headband, John Lennon sunglasses. And she's wearing a peace necklace. What does that look like? Is that a Mercedes symbol or a peace symbol? How does a peace symbol look? What? Oh, this goes all the way down like that. So, are you understanding the stereotype I'm trying to get at here? Yeah, she's going around planting trees. Okay, so her name is Star Lily. Okay, Star Lily is planting trees. My friend actually went to high school with a girl named Rainbow Star Plant. That is not conservation. She might think of herself as a conservationist, but if you're adding to the number of trees, you're not conserving the number of trees. Conservation means keeping things exactly the same. So if she really was a nature conservationist, she would just wait in the forest until she heard a tree fall down. And then she would run over and plant one tree and then wait for the next one. Okay? So that's what conservation is. It means keeping things exactly the same. Did I really have to draw that elaborate picture for that? Probably not. Okay, so we are going to talk about conservation of energy. And what it means is, as time goes by, total energy stays exactly the same. And really, that's true in general. There's a set amount of energy in the universe, and if energy leaves one thing, it goes to something else. If it disappears from being viewable in one way, it's viewable in another way. That's not really what we're talking about in this class. So this is true in general, generally. But in this class, what we'll use is conservation of mechanical energy. And conservation of mechanical energy, let's say, only holds under very specific conditions. So I think that's sort of a confusing thing about this topic. The idea that total amount of energy in the universe stays constant, that's true. But we're not looking at every kind of energy in the universe. We're only looking at mechanical energy. And that is not always conserved. Like, for example, if you take a piece of Play-Doh and slam it down onto the ground and it splats on the ground, there's energy from it flying through the air really fast. When it hits the ground, that energy goes into deforming the ground, deforming the Play-Doh, making noise, warming up the Play-Doh a little bit. So that energy is still conserved. But speaking in terms of mechanical energy in that case would not be conserved. So I'm going to try to be really clear as we talk about this, what things are required for these conditions to be met, you know? Conservation of mechanical energy is a special case of a more general law called the work-energy principle. And the work-energy principle says that if you add up all the work done, we don't know what work is. I'll have to talk about all this stuff. But let me just give the equation first. Add up all the work that's done on a chosen object. That's equal to the change in something called kinetic energy. So work total is the sum of the work done on the chosen object by each force acting on the chosen object and delta KE is the change in kinetic energy of the object. Okay, so before we can use this equation, I have to define what work is, and I have to define what kinetic energy is, and then we'll start putting this together. And then our overall, so approach, I guess, is first we're gonna talk about the work energy principle. That's going to require defining work, defining kinetic energy, and then second, I'm going to talk about when, like under what conditions. The work energy principle simplifies to conservation of mechanical energy. Okay, so for the work energy principle, I'm going to start by defining work. Work is energy added to an object by the application of a force. So there are other ways to add energy to an object. The most obvious, or the clearest other way to add energy to an object besides applying force to it is to add energy to it by putting it in contact with something of a different temperature. So like if you take a object, a piece of metal or something, and put it on the stove and light the stove, that thing gains energy because of the big difference in temperature. And energy goes into the metal object as the fire raises its temperature. We're not talking about that way of adding energy. We're talking about the energy that something gets if you apply a force to it. Like, so for example, if a baseball is pitched in and somebody hits it with a bat, the bat applies a force to the ball, and that application of the force to the ball changes the ball's energy. And its energy is related, we'll talk a little bit more about what that energy is, but as the ball's speed increases, that means its energy is increasing. So as an object moves from position P1 to P2, it has a displacement vector D that's equal to P2 minus P1. Let me draw what that looks like. So if an object goes from here to here, so say this is position 1, this is position 2, this vector here is the displacement vector. Then the definition of the work is the force vector, and then there's a dot. This is a mathematical operation you can do with vectors. So dot displacement vector. This is called the dot product. And the meaning of that is you take the x component of the force and multiply it by the x component of the displacement. And then you take the y component of the force times the y component of the displacement, and you add those two together. So this is the mathematical definition of work. And the intuitive meaning of work, sort of the intuitive result, is that if the force and the displacement vector are within 90 degrees of each other, then the work is positive. And that means energy is being added to the chosen object. That's the first thing. Second, if the force and the displacement vector are more than 90 degrees apart, and W is negative, and it means energy is being removed from the chosen object. And third, if the force and the displacement vector are exactly 90 degrees apart, the work is zero, and it doesn't cause a change in energy. Okay, so let's think about some cases. Okay, so the first example, let's say that we're looking at a top view of a box sliding on ice. So let's say that, so here's the box in the top view. And let's say it started here at P1, started here at P2, ends here at P2. And let's say the whole time that it's moving, you know, it's going this way. So while it's moving, a force is applied in this direction. So is the work positive, 0, or negative? And is energy added, added to or removed from the box? So this is a case where the box is sliding from P1 to P2 and somebody's behind the box pushing on it, okay? The displacement vector goes like this. There's the displacement vector. The force vector is in this direction. Are those two vectors more, less, or equal to 90 degrees apart? Yes, they're pointing in the exact same direction. There's a 0-degree angle between those two vectors. So F and D are the same direction. So they're less than 90 degrees apart. So would work be positive, negative, or 0? Positive. Anybody have any questions about that, first of all? Those two arrows are within 90 degrees of each other. They're the same direction in this case. And so W is positive. If W is positive, is energy increasing or decreasing for the box? Yep, so energy is increasing. And now think physically about what would happen in this case. So if our coordinate system is in this, this is our coordinate system. In that plane, the only force acting on this would be the person pushing it this way. The box is sliding from here to here. Will this box be speeding up or slowing down? Speeding up because the box is already moving in that direction and a force is making it accelerate in that direction. That force would make the box speed up. So you see a connection between the box speeding up and the box gaining energy. Okay, so that's what we're going to keep seeing, that increasing something's energy, if you're only talking about mechanical energy, is related to making the thing's speed increase. Okay, before I go on to another similar example, anybody have any questions about that one? So now, same thing. There's P1, Here's P2. And the box is going this way. Or same, I don't know, setup. But this time, the force is this way. Okay, so the displacement vector is still this. The box is still moving from P1 to P2. The force vector now is going the opposite direction. So are the displacement and the force vector more or less or equal to 90 degrees apart? More. Yep, they're in opposite directions. It's a 180-degree difference. So the displacement vector and force vector are 180 degrees apart. So now, is the work positive, negative, or zero? Yep, work is negative. If the work is negative, is the box's energy increasing or decreasing? Yep. So the box's energy is decreasing. And now think about the speed. So in this case, we don't know what made the box start to slide, but something made the box start to slide from here to there. And we know it still starts here and ends here no matter what this person's doing. You could think of it as like maybe it's going really fast here and that force isn't enough to stop it. Okay. But now what is that force doing? Is it making the box speed up as it goes from here to here, or is it making the box slow down? Right, now that force is fighting against the box, you know, the person's pushing this way on it, trying to make it stop. And so the box is going to be slowing down due to that force. And so, again, we see this relationship between energy and speed. If the energy is decreasing, the speed is decreasing. So that force in the opposite direction of the motion would make the speed decrease. So again, you see that connection between speed and energy. High speed and high energy are related to each other. Low speed and low energy are related. Anybody have any questions about that example? Yep. Yeah, because if you, so they start out in the same direction, they get up to, they get up to 90, then they keep going to get to 180. And once they pass 180, you can just take the angle the other way. You know what I mean? So it goes 178, 179, 180. Now it's 179, 178, 177. So yeah, 180 is the maximum they can be apart. Who's having fun so far? Good. Kind of. Good. Okay. The rest of you should try to be more like them. Okay, so here's the third example. So now it's not ice. Now it's like an object on a track. So here's P1. Here's P2. The track goes between those 2 points. And then there's this object going this way along the track. So the idea here is it's on a track. It can't leave the track. Okay, so you can try to push it off, but it's not gonna leave the track. Okay, all it's gonna do is go between P1 and P2. And in the case that we're considering, it starts at P1 and goes to P2. And this time a force is applied perpendicular to the track like this. Okay. So now the displacement vector is this. The force vector is this. What's the angle between the force and the displacement? If those two are perpendicular to each other, is the work positive, negative, or zero? Yeah, work is equal to zero. If work is equal to zero, is the energy increasing, decreasing, or staying the same? Yep. And now let's think about that relationship between speed and energy. The energy change stays the same. Now imagine, this is a little harder to imagine because friction means that it would be hard to do this practically. But imagine that you were going, so this is going some speed, okay? Say it's going 5 miles per hour. And imagine somebody just running along the side of that box, pushing it this direction. Okay? But imagine there's no friction. We don't want to think about friction and stuff yet. What would that do to the speed? Just pushing the box this direction. If there's no friction. It wouldn't do anything. It wouldn't be trying to accelerate it in the opposite direction, which would slow it down, or accelerate it in the same direction, which would make it speed up. It would be trying to push it in a direction it can't go, that it's not going. And so the speed would stay exactly the same. Its speed in this direction doesn't have anything to do with forces in this direction. And so again, you see that relationship between the speed of the object and the energy of the object. If the object's energy is staying the same, the speed has to stay the same. So in this case, the object's speed would stay constant. And again, you see the connection between the object's energy and its speed. Any questions about any of those yet? Okay, so now let's talk about kinetic energy. Let m be an object's mass, and capital V is the object's speed. Then the object's kinetic energy Ke is equal to 1/2 times the mass times the speed squared. If you have the object's velocity vector instead of its speed, you can calculate it as kinetic energy is equal to 1/2 times the mass times the x component squared plus the y component squared of the velocity. Those are equivalent. Sometimes one's easier, sometimes the other one's easier. Units for energy. This is true of kinetic energy and any other type of energy, are always equal to force times length. And so the SI units are newtons times meters. And since you can write newtons multiple ways, you can also write this as kilograms meters squared per second squared. And this unit, you can think of it as a newton times a meter or a kilogram meters squared per second squared is equal to a joule. And you abbreviate it with a capital J. Notice, by the way, that this form comes straight from the definition of kinetic energy. I mean, these two ways of writing the units are equivalent, but kinetic energy is 1/2 times the mass times the speed squared. Mass is kilograms, speed squared is meters squared per second squared. So you can get that from the definition of kinetic energy. If you ever forget. Okay, so a couple things to notice about energy. First, energy is a scalar quantity. It doesn't have direction. So when we were talking about the work that a force was doing on a box as it moved along, we weren't talking about our answer for work as a vector. We were just saying it's positive or negative or zero. Okay, so energy is a scalar. It's just a number. There's no direction associated with it. There was one other thing. I don't know if this is it, but this is important too. Energy increases as an object speeds up. And decreases as an object slows down. Okay, well, let's do a couple of examples. So let's say there's a person on an elevator. The mass of the person is 50 kilograms. And the elevator is moving up at a constant speed of 4 meters per second. As the elevator rises 10 meters, we want to calculate first the work done on the passenger by gravity. Second, the work done on the passenger by the elevator. And since those are the only two things, those are the only two forces acting on this guy, if we did a free body diagram, there'd be a weight force, and then there'd be a force pushing up from the elevator. So combine these two now and calculate the, well, let me call it the total work on the passenger. And then based on that, what's the change in the passenger's kinetic energy? Okay. So first, let's think about this a little bit in terms of what we already know. One thing we have to do is figure out the force vector that's applied to the passenger by the elevator. That's not given. So let's think about a free body diagram first. So there's what forces are acting? There's a downward force of gravity. The magnitude of that is the person's mass times 9.81. So 50 kilograms times 9.81 is 490.5. And then there's a force pushing up from the floor of the elevator. I'll call that N. And now let's use Newton's second law, and we can figure out what that force N is. So the forces are 0, negative 490.5. The normal force is 0, positive N. And that's equal to the mass times the acceleration. What's the acceleration of the passenger? 0. Yep. The speed is constant. He's moving in a straight line, so the acceleration is 0. Anybody have any questions about that relationship? He's moving with a constant velocity. Constant velocity and 0 acceleration mean the same thing. So equals 50 times 0, 0. The y equation then says N is equal to positive 490.5. And so the force on the passenger by the elevator is equal to 0, positive 490.5. Okay, so now we know each of those individual forces. This is the force vector applied to the guy by gravity, and this is the force applied to the guy by the elevator. And we're going to use those in parts A and B. So part A, we're trying to figure out the work on the passenger, the work done on the passenger by gravity. Well, our force vector from gravity is 0, negative 490.5. What's the displacement vector if he rises 10 meters? What? Yeah, so, and it's a vector because it's a displacement, so it would be 0 in the x direction, positive 10 in the y direction. Now the work you get by multiplying the two x components together and adding that to the two y components multiplied together. And you get a work of negative 4,905. And what are the units? Joules, yep. Is energy, so now these two forces are, they don't have to do the same thing, but just looking at gravity, is gravity adding energy to the passenger or removing energy from the passenger? Removing, because of the negative. Okay. I mean, What that means is if this guy's going up 10 meters and the only force on him was gravity, would he be speeding up or slowing down? Slowing down. If he's on the way up, gravity would be slowing him down. Okay. So now we're going to do the same thing with the force applied to the guy by the elevator. The force on the passenger by the elevator is 0, positive 490.5. Does the displacement vector change? It's still the same guy going through the same motion, so this is just equal to 0, positive 10. And so the work, and actually on this W up here for part A, I'm going to write work due to gravity, just to distinguish these. This is the work done by the elevator. So the work done by the elevator is 0 times 0 plus positive 490.5 times 10. And you get a value of positive 4,905. So gravity removed 4,905 joules from the passenger. The elevator, the floor of the elevator, added 4,905 joules to the passenger. So now the work energy principle, part C, we want to know what the total work is. That's the work done by each of those individual forces just added together. So we have negative 4,905 plus positive 4,905 is equal to 0. So the total work done on the passenger is 0. So no change in the passenger's energy. And so from this analysis, we can see that the speed stays constant through the motion, which was given at the start of the problem, and we showed that that had to be the case if those are the forces applied. Okay, so let's do one now where the same kind of thing, but now the elevator is going to be accelerating upwards. Okay, so its speed is going to be increasing as it goes over these 10 meters, right? If its speed is increasing, what do we expect to have for a total change in energy? Do we expect it to be positive, negative, or 0? All three options were brought up. That's good. But so if the speed increases, the kinetic energy increases. So the work has to be positive. You need positive work to get an increase in kinetic energy. Okay, so now it's the same as above. But the elevator accelerates upward at, let's say, 1 meter per second squared. Well, the first thing we have to do is figure out the force that's applied to the passenger. So we'll start with a free body diagram. Yes. Well, we did find that there's no change in the passenger's kinetic energy. Okay, so what forces are acting on the passenger in this one? Yep, there's a weight force of 490.5. Yep, and a normal force, exactly. So that doesn't change. But Newton's second law changes a little bit. We have a downward force of 0. Well, we have a force 0, negative 490.5. That's the weight. We have a force 0, positive n. That's the normal force. And that's equal to the mass, 50, times the acceleration vector. It's accelerating upward at 1 meter per second squared, so that's the acceleration. And so the y equation says n is equal to positive 540.5. In other words, if he's accelerating upward, the floor has to be pushing a little bit harder on him. So the force vector on the passenger by the elevator is 0, positive 540.5. Okay, so first, what's the work done by the elevator? Weight was the one we did first. What's the work done on the passenger by gravity? So the work done on the passenger by gravity is equal to the dot product of the force vector and the displacement vector. So we have 0 times 0 plus negative 490.5 times positive 10. And we get negative 4905 joules. Any questions about that? So that's the same as it was in the last example. The next one is going to be different, though, because we have a different force. So now the work done on the passenger by the elevator the x components multiplied together, 0 times 0. The y component of the force applied by the elevator is 540.5. Y component of the displacement is positive 10. And so this is positive 5,405 joules. And so the total work done on the passenger is negative 4905 plus 5405 or 50 joules. $500. Yeah. Wait. Yes. Wait. Right. Thank you. Okay, so now when you add up the work done by all the forces, you get a positive answer. So is the person's kinetic energy increasing or decreasing? Increasing. So is the person's speed increasing or decreasing? Increasing. Okay. And if you knew what the starting speed was, you could use the definition of kinetic energy to calculate the final speed. So for part D, the change in kinetic energy is equal to 500 joules. And this is actually, pretty useful for certain problems. Using Newton's second law, we could do things where we calculated something's acceleration, but that didn't let us calculate what the speed was after it had moved a certain distance. This new thing that we're able to do using the work-energy principle is to figure out if this object moves, in this case 10 meters, with these forces acting on it, and it starts at this speed, what's its speed going to be at the end of that motion? Okay, so it's sort of a similar but different problems that we're going to be able to solve now. Okay, quiz on Thursday.